Hey everybody, so this is the solutions to Worksheet 1.3. Here we're focusing on identifying functions as well as identifying domain and range of those functions. In number one, we are given two different relations. Both of them are expressed as a set of ordered pairs, and we're asked to determine if they in fact represent a function of x. So what we're going to do here is we're going to rely on our definition of a function, and we're going to check to see that each x coordinate goes to only one y coordinate. And if we can show this, then we've got a function in our hands. So if we look at a in number one, what we would notice is that, well, x equals -3 goes to 9, x equals 9 goes to 3, x equals +3 goes to -9, and x equals -3 goes to -9. So that shows the mapping of the x's to the y's. The thing that we're going to want to watch out for here is that we notice that when we have -3, it's going to actually two different y values. So since x equals -3 goes to y equals 9 and y equals -9, so we've got one x going to two different y's, then this is not a function. So that's one way that we can go about checking that. So that takes care of A. So let's apply that sort of reasoning to B. So if we look at this, let's go ahead. We've got some more points. So I'm going to go ahead and identify the x's and then identify the y's. So all of the x's that this relation uses is -3, -2, -1, 0, +1, +2, and +3. And if we look at the y coordinates that each of these x's go to, well, we've got x equals -3 going to +9, -2 goes to 4, -1 goes to 1, 0 goes to 0, 1 goes to 1, 2 goes to 4, 3 goes to 9. And we see that every single one of these x's is only going to one unique y value. And since there's no overlap, since there's no sort of pairing off into two different places, we have a function. So we can go ahead and we can conclude that since each x goes to only one y value, then we do have a function. So this is a function. Okay, so that's nice, but we've got a little more work to do because of that. So in the directions, we were asked to find the domain and range of the relations that didn't, in fact, become functions. Well, domain and range isn't too bad. What we're going to consider is that domain is simply the collection of all the valid x values that our function attains. And in this case, we can just kind of go through and make a set of all of those. So we've got -3, -2, -1, 0, +1, +2, and +3. So the set of those numbers, that represents our domain. So again, these are just the x's, and they represent the input of this particular function. For the range, we're going to turn our attention to the output of the function, or the y values, and those are the ones that we underlined in blue. So for the range, we're going to look at the set that includes +9, +4, +1, 0, +1, +4, and +9. So this is going to be all of our y values, and this is the output of our function. So that takes care of number one. Okay, so for number two, we have a similar task on our hands, except in this case, the relations that we're given are displayed as graphs, but we're still asked to determine whether or not it represents y as a function of x. So in order to do this, we're going to take a slightly different approach, and we're going to use something called the vertical line test. And the vertical line test tells us that if we've got a graph and we can draw a line that hits the graph in more than one spot, then it is not a function, or it fails the vertical line test. So this is illustrated pretty nicely in this first one in part A. So we look at it, part A, we've just got a graph of points going on here. But if we were to draw a vertical line directly through x equals -3, what we see is that this hits our curve or our graph in two different spots. And because of this, we could say that we can note that when x is equal to -3, well, in one case, y takes on a value of 0, that lower point. And in another instance, y takes on a value of +1. So here we have this idea of 1x going to two different y values. This is indicated by the fact that it fails the vertical line test, which I'll abbreviate as just VLT. So this tells us this is not a function. So a pretty nice, easy way to graphically display this idea of a function. If we look at part B, we can kind of imagine we've got a parabola here. Is there any way for us to draw a vertical line that's going to hit this curve more than once? And it's not going to happen in this case. So because of that, we would say that this passes the vertical line test, and as such we can conclude that this is a function. So that's all that we needed to do. But since we do have a function here, one of the things that we were asked to do is find the domain and the range of the relations that are functions. So we're going to go ahead and we're going to do that. So let's start by thinking about the domain. Now we talked about domain in the first problem as sort of the set of all the x coordinates. Graphically, another way we could think about this as sort of a projection on the x-axis. I'll explain what that means in a second. So projection on the x-axis. And one way we could think about this is this would be as if we looked at our curve and we were just sort of taking all of the points and casting a projection or a shadow of it onto the x-axis. So we take all of these points and we would just compress them down onto the x-axis, almost like flattening it on the x-axis to see where the curve is defined on the x-axis, which would give us all of the points in our domain. So if we were to do that, and I'm just going to go ahead and highlight it, we can imagine that all of these points would drop down and cover the entire x-axis. So this red line right here is a projection of our curve, this parabola, on the x-axis, and this gives us a visual of what our domain is, and in this case it's the whole x-axis. It's all real numbers. I'm going to go ahead and write this in interval notation and say, well, that means that our domain is going to be all x values between -infinity and +infinity, basically all real numbers. Now we can do the same thing for range. Go ahead and switch over here just to make it a little more clear. So for the range, before we talked about it was all of the y values, but if we wanted to think about it in terms of the graph, it's the projection of the graph on the y-axis. So it's the projection on the y-axis, and that gives us all of the y values that this curve takes on. Now if we think about this, if we dropped all of these points and just sort of brought them straight over to the y-axis, all of these curves, just sort of compressed it, smushed it horizontally onto the y-axis, what we would see, let me get these arrows out of the way, is that we would have a projection that starts here at y equals +1 and would extend all the way up the y-axis. So this blue line represents our projection on the y-axis, and in turn is going to give us our range. So we could go ahead and say that the range is going to be all points from +1, including +1, so we use the bracket, all the way up to y equals +infinity. And this is the way that we can determine our range. So let's go ahead and now move on to part C and part D. So C looks pretty suspicious right off the bat here. Lots of places we could illustrate this, but if I was to drop a vertical line down here through x equals -2, we would see that this fails the vertical line test. It hits it in 2 different spots. So this relation fails the vertical line test, and we can conclude that this is not a function. And since it's not a function, we don't have to worry about the domain and the range. For this last graph that we've got, we could try and draw vertical lines to see if it fails, but with just a little bit of work and observation, we see that this is going to pass the vertical line test. So this means that we have a function, which also means that we now have to address the domain and the range. So let's do it like we did with part B and think about the projections on the x-axis and the y-axis. So first we'll start with the domain. And if we were to take this curve and do a projection of all these points onto the x-axis, then what we would see is that we would have a solid point here, and I'm going to put the open point here, and then all of these points, since there's an arrow that is suggesting this is going to continue to go off infinitely in both directions. So these two red lines on the x-axis are illustrating where our domain would lie. So now we've got to go ahead and express this in some way. I would look at this and I would say, well, starting in the negative end, we're going from x values from negative infinity all the way up to and including 0. So that's sort of that first line from negative infinity over here all the way to the origin. And then it's going to pick up again with the second interval. We start at 1, but we're not going to include 1. We notice that there's an open hole in our curve there, so we're not going to include it, but everything right up to it. So we'll use a parenthesis to indicate that. In case that's not clear enough, I'm going to redo that. So that's a parenthesis with 1, and then this is going to extend off to positive infinity. And since we want to bring these two together, we're talking about the union of these two intervals, so we'll put that union symbol right there. So that would represent our domain. Okay, so for the range, let's get all this stuff out of the way. So for the range, we're going to be considering our projection on the y-axis. So let's start with this top point. Now if you think about this, with this part of our curve, if we were to project that perfectly over to the y-axis, all this would look like is it would reduce down to just 1 point. That whole line would just project as 1 point. So that's what we would get from that part. And then if we were going to take this other part of our curve and project it onto the y-axis, this point at 1 would stay there, and then all of these other points on our curve would just get mapped over to the y-axis like this. And that would give us our y-axis projection. So for our range, we'll go ahead and we'll start down here at negative infinity for y. And it goes from y values from negative infinity all the way up to y equals positive 1, which we are including with the solid dot, so we'll give that a bracket. And we just want to add this 1 point, y equals positive 2. One way we could do this is we could just write 2 and write it as a set of just one number. So those are our braces, or those curly brackets that we use to represent sets. Okay, so for the last problem, number 3 on this worksheet, we're asked to determine whether or not the equation that we're given represents y as a function of x. Still the same basic idea. This is going to represent a function if we know that each x we choose goes to only one y. And the nice thing about this is that the x's and the y's are spelled out, pretty straightforward for us. For part A, if you can't see it right away, one thing you could think about is, well, if I pick any x and I plug that value in, will I only get one y value back? So just sort of to check this idea is, let's just try some examples. If I were to pick, say, x equals 1, if I did this, what would happen? Well, I get y is equal to 1 cubed minus 1, and this would end up giving me 0. So I picked an x, and I only got one y value out of it. It didn't give me 2, it didn't give me 3, it just gave me one specific y value. And we could do this for basically any one. We'll do another one just to kind of reiterate this. But if I plugged in x equals -2, and then we would subtract -2 from this, this would end up giving us, what, -8, and then plus 2, which would give us -6. So again, by picking an x value, plugging it into the function, I only got back one y value. And we could see that that's going to work out. No matter what you pick for your x, you're only going to get one y value back from this. So because of that, we know that we have a function. Okay, so what about part B? What you might want to do with these, if it gets a little bit more complicated than we saw in part A, is a good first move with problems like this is to go ahead and first solve for y. If it hasn't been solved already, like it was in part A, it's probably a good idea to do it here. So let's go ahead and do that. So I'm going to go ahead and I'm going to subtract 2x from both sides. That'll give me 3y is equal to 4 minus 2x. And then I'm going to go ahead and I'm going to divide both sides by 3. And when I do this, my function is now going to be y equals 4 minus 2x divided by 3. Now, I'm going to spare you the testing points, but if you don't see it, you could definitely try that. But we can see that if I put an x value in right here, any value for x, and I do all the calculations, I'm only going to get one value back for y, whatever that number happens to be. So we can clearly see here that each x that we choose goes to only one y. So again, in this case, we have a function. So we can check that one off. In this last one, getting a little more complicated, but let's go ahead and do our first move. Let's solve for y. And this will get a little more complicated. I'm going to go ahead. You could do this a couple ways. I'm going to go ahead and keep the y on the left here. So I'm going to subtract x squared from both sides, which is going to give me minus y squared is equal to 1 minus x squared. Order of operations dictates that we need to actually, since there aren't parentheses around this y squared, we need to get rid of that negative first. So the next thing that I'm going to do is I'm going to multiply both sides by -1. So if I multiply negative y squared by -1, that's going to give me y squared. And if I multiply, let me go ahead and write this one out. If I write -1 times 1 minus x squared, we go ahead and we distribute that negative to each of the terms, and we get y squared is equal to -1 plus x squared. And just to get this in a slightly more appealing order, we could write this as y squared is equal to x squared minus 1. The last thing we've got to do here to solve for y would be take the square root of both sides. So if we take the square root of both sides, this is where we need to be careful. If we take the square root of both sides, we're going to see that y could be equal to plus or minus the square root of x squared minus 1. Now the reason this is important is now we've sort of set up a case here where I could pick a value for x, and all we need is one value to prove that to prove our point here. But if I picked, say, x equals 2, so let's just kind of see what happens. If I tried x equals 2, so I'm going to pick that one x value and see what happens when I plug it into this function. If x equals 2, this is going to be y is equal to plus or minus the square root of 2 squared minus 1, which is going to be equal to plus or minus the square root of 4 minus 1, which is going to be equal to plus or minus the square root of 3. So let's think about what this has actually told us. When x is equal to positive 2, this implies that y could be equal to positive square root of 3, or it could be equal to negative square root of 3. So we've got one x value going to two different y values, so this is not a function. For that reason, one x value goes to two different y values in this case. Okay, so that should do it for these solutions, and I'll see you all in the next video.